we'll continue now with the story regarding the moduli spaces. So last time we stopped here, I believe, where we were talking already about the nitty-gritty of the moduli spaces of quantum tori. So just as the moduli space of tori, classical tori, would be related to the moduli space of lattices, classical lattices, well, the moduli space of calibrated quantum tori should be related to the moduli space of calibrated quantum lattices. And here, by calibrated, I mean that when the slope of the foliation that generates the quantum tori, the chronicle foliation that generates the quantum tori, is irrational, then, well, nothing, there is no interesting phenomena. The problem is when the slope is rational, ironically, and then you have a Hausdorff quotient. But this Hausdorff quotient, imagine a two-dimensional torus, and imagine this irrational foliation, linear foliation, chronicle foliation, and then imagine that it becomes rational the slope, and then the leaps become these torus knots, and the quotient by the torus knots could be a circle, and then all of a sudden you would have a one-dimensional object, and this would seem contradictory because you have all the time homotopically two-dimensional objects. When the slope is irrational, the leaf of the foliation is this thing that winds all over the torus densely. Every leaf winds densely all over the two-dimensional torus, but it's contractible. So the quotient homotopically should be just a two-dimensional torus. The Borel construction of that group action of R on the torus, when the slope is rational, is just the action of a contractible group. So it's a two-dimensional object. So you could jump from one-dimensional objects in the rational case to two-dimensional objects in the irrational case. And you don't want to do that. It would not give you a nice moduli space. So what you do is that you pump up the dimension of the rational case by one by adding by remembering the stabilizer of the action. It seems that it is this torus knot acting on the two-dimensional torus what is going on. But if you think about it, it was a real line winding on the torus knot. So there was a stabilizer of Z. If you take into account this stabilizer of Z, then you don't quite get a circle as a quotient. You get some sort of a normifold of a circle with a Z stabilizer at every point. And as a stack, it's the classifying. It classifies. It's classifying the space, underlying space, is again a two-dimensional torus. So it's again a two-dimensional object, and all these invariants like Hochschild homology, etc. will look at a two-dimensional object. So well, this can be implemented by considering calibrated tori, that is adding this germ, this stabilizer, everywhere as I vary the slopes of the foliations. And this can be implemented technically like in this definition. Here again, the basic idea is that, let me look at, well, let me search very quickly for the picture. The picture is here. This is a picture of a calibration. Here you have a higher dimensional lattice. Typically n is bigger than.
We don't see anything.
You don't see it?
No, the screen is not shared.
Nothing. Yeah. Or avatar.
Oh my God! Something happened when I changed the. Now you can see it again?
Yes.
Sorry about that. But this is the relevant picture. Here you have a bigger dimensional lattice. Here is your. This you can think of this RD. You can think of it as the real part of the tangent space to the identity of the torus. It's a d-dimensional space, so it will be a d-dimensional complex torus when the action occurs, but it's only the transversal to the foliation. So I have this higher dimensional lattice, typically n is bigger than d. I have this map H, and this dust that appears here, that typically will be dense in RD, is called a quasi-lattice. And this dust that appears here is the transversal to the foliation. So you imagine that you wind this RD into a d-dimensional torus, but this is only there is one more dimension, a d plus one dimensional torus, and this is just the holonomy. It's the image of the holonomy of the Kronecker foliation in higher dimension. So again, technically, well, the H goes from Zn to Rd. N is typically bigger than D, and J is a purely combinatorial object. It's just a subset of the indices. And this is going to play the role of the mark points of the modular space, just like in the modular space of curves. You get a more regular, a nicer modular space. Here, the same will happen. If I mark some of these indices here, I will get a nicer modular space. Anyway, I am required to, I require that they generate RD, the images of these vectors, the ones that are not marked, generate RD. And well, that's it. This is a calibrated quantum lattice. Is this morphism?
But still you can have more, right, of these generating vectors. Even outside of this big J, you say vector, this the span of these vectors outside of J, it's generally it's bigger, right, than D.
No. All the image of H is RD.
Sure, but no. The question is if J n minus the cardinality of J is exactly D, or it can be bigger.
No, it can be as large as you want.
Okay.
And this is an important remark in examples. Maybe in 2 talks you'll see what I mean by this. But this generates a tower. I can always just add here Zn plus 1, Zn plus 2, Zn plus 3. And here just have these things adding to J more and more elements. And it would generate an interesting tower of objects. Yeah. Well, it's also useful to know what is a morphism, and a morphism is the obvious thing, is a morphism. Also, the choice of the letter H, before I go to morphisms, the choice of the letter H here is because H is the Planck's constants. We have n Planck scales in this quantum system. You can imagine various quantum harmonic oscillators, n of them, and they will, but of course in physics you think of a universal Planck's constant and that's it. But mathematically nothing stops you from thinking that each one of them live on a sector of the universe where there is a different Planck's constant, Planck scale. In any case, these decides n different Planck scales of the quantum system that we were going to produce. So that's why we chose the letter H here. In the case D equals 1, D equals 1, n equals 2, and D equals 1, typically H of 0, 1 is 1, and H of, 1, 0 is 1, and H of 0, 1 is H bar, the classical Planck's constant, and then you will recover the classical quantum harmonic oscillator and so on and so forth. So H is constituted by of Planck constants. So well, now a morphism is a pair, you know, of L R to R D prime linear, H Z to Z and prime Z linear, and then of course this is an arithmetic object. This is an arithmetic object. So that there is a combinatorial object, of course, a combinatorial mark point thing. And then, well, we have the obvious conditions. Gamma, gamma, I didn't say it here, did I? How careless. Gamma will be the notation for the image of H. Gamma will be our notation for the image of H. This dust in RD will be gamma. So I want L gamma to be inside gamma prime. I want LH to be H prime H. I want for the I not in J, this to be in the generated product I not in J, and for the I in J, I want, and this is the basis vectors, the canonical basis vectors of set to the M. So for the I in J, I want H of EI to be E of SI, where S is this combinatorial object. So, well, it looks longer and more complicated than what it is. It's the obvious thing that it should be. And in the picture, more or less, the situation is depicted. So, but let's do an example. Suppose that H of XY, Z2, goes to X plus Y square root of 2. And here, I should be very tempted to write H bar here, but I will write square root of 2 because it's an example. So one thing is rational, the other thing is irrational. This corresponds to an irrational slope Kronecker foliation on the torus. This corresponds to that quantum torus of the two-dimensional torus with a Kronecker foliation of slope square root of 2. J here is empty. We don't worry about J. And here, of course, this is inside of RD equals 1. So the dimension of R is equal to 1. And then, well, here we have so we are going from this quantum torus to this quantum torus, and we can produce a map from the quantum torus to itself. These endomorphisms of the quantum torus are going to be important for us. So remember that a mapping was a linear mapping from R1 to R1, and H it has to be a matrix from Z2 to Z2. So it's an integer matrix from Z2 to Z2. I'm going to do this integer matrix from Z2 to Z2. And this is going to be L. L, remember, is just a linear mapping from R1 to R1. So, well, here it is. Z2 to Z2 goes like this. H sends Z2 to here, the bigger lattice to the R1, the bigger lattice to R1, to gamma. This is gamma. This is gamma. This map, sending Z to Z square root of 2, well, it sends gamma to gamma. And this is L sending gamma to gamma. So this is the identity map, you know. This is L of t equals square root of 2t. So, or is this map exactly? This is L. This is L. Sending Z to the square root of 2z. This is L. L goes from R to R, but it can be complexified. Here is going from the gamma to gamma. I just take the same matrix and the complex numbers. And this descends to C mod gamma, C star mod gamma, C star mod gamma as a stack. And then I have managed to produce a very beautiful map called Z goes to Z to the square root of 2. So I have these beautiful maps that are purely algebraic, quotation, maps of the quantum torus, but now the powers are irrational numbers. And this is a new feature of this toric geometry, this quantum toric geometry, that the monomials in this quantum toric geometry admit irrational powers. You see what I mean?
Not exactly. So I don't quite understand in the lowest level where is the trace of this square root of 2 quotient. So I see. So you actually take the quotient by the multiplicative group generated by square root of 2, right?
That's right. That 1 plus square root, yeah.
Okay.
Mm-hmm.
No, like C star is the quotient by the group generated by 1.
Mm-hmm.
And then, well, not square root of 2. Yeah, okay, I see.
Yeah. So you see, typically in toric geometry, you have these monomials that allow you to glue charts. Or you can see it also as typically in toric geometry, you have these monomials that allow you to glue charts. You can also think of it in tropical terms, but in toric geometry, you have these monomials with integer coefficients that allow you to glue charts. And then the torus acts because these are just monomial gluings. Here, these are the generators of the monomials. These maps that I just wrote is one typical generator of a monomial that will allow me to glue charts. But now the exponents will be irrational exponents because the slopes of the fan now will be allowed to be irrational. So, well, obviously, the simplest quantum fan is in dimension 1, and if I put here h rather than square root of 2, notice that here I wrote h rather than square root of 2, because this was h. But h was completely determined in this case by this square root of 2. I could put here a number, h bar, and then in any case, if I put that number h1, I would have the quantum lattice rather than the canonical lattice in R that would give you C star, R by the integers. Now I could have the canonical lattice in R, and I do the same combinatorial fun, but now I put this quantum lattice rather than the classical lattice. And what I will obtain is CP1 H bar if you want. So, but of course, now I can move this number. Now I can move this number and I can move this diagram as I move this number. No problem. No problem. And I could get a modular space of projective lines. I don't know if you see what I'm trying to say here.
Yes.
Okay, so now I would get that. So these are quantum funds. A more general quantum toric stack can be constructed starting from a general, not necessarily rational quantum fund. Such a quantum fund lives in a quantum lattice, you know. Now there is this image of H, that is gamma, inside of RD, typically dense inside of RD. And then there is this quantum torus, ZD mod gamma, and I can promote it to a calibrated quantum torus, but let's not worry about that for now. Let's think of it just as a quantum torus for a second, CD mod gamma. Remember that I'm looking at the transversal, I'm looking in this drawing at the transversal of the torus and the holonomy of the foliation. And this is a transversal cut, and then I take it so kind of universal cover. And the quantum toric stack given by this fan, this quantum lattice. And I will explain the notation B. That is, I should have written H, but it was an evolving notation when I wrote this. V is an equivariant compactification of this. Well, it's also better to write here H rather than gamma. So H is really much better. This was the first, this is the first intuition, you know, to talk about this, marking these points here or here to try to keep track of what's going on here. But then you realize that H is really the way to go. The morphism, H in this case, H is really the way to go. This is the H, these Planck constants are going to be the natural, just like in quantum theory, H bar. H is going to be the natural deformation parameter for all this story. H is going to give you the natural charge for the modular space of toric varieties. So here is H, and this is a calibrated quantum fan, and here there is a little bit of J. I could mark this point and this point, and maybe not mark this point. And marking some of these points, I would get a full calibrated quantum fan. And it determines various Planck lengths on the quantum system. So you are meant to imagine that this is truly microscopic.
So I don't quite understand. I thought the role of this marking space, this quantum lattice, and then you have some more points that you mark. What they are corresponding to?
Well, I just have this additional freedom to mark points, just like in the modular space of curves.
Okay.
I just mark some points on the lattice, and I carry them around.
Okay, but this doesn't correspond to this calibrated data. It's some more thing
No, it does correspond to the calibrated data.
I thought calibrated data was, so where exactly it comes to the game? So I thought you have this H, and your marks points, how they are related to this H. These are generators, these are images.
I could add Z plus 7 here. I could add 7 dimensions here, N plus 7.
Yes.
And just use those 7 additional vectors to mark some points on the same lattice.
Okay, but these marked points that you considered in this later picture, those correspond to the images of the generators of Z to the N, or what?
Yeah.
Okay.
Yeah, in this picture may not be entirely clear, but these are the images of these things. Of course, these are many of them, and I just drew 3 here.
Okay, got it.
Yeah, but it's kind of silly. Like, I don't have enough dimensions to, but it was meant to be that. Yeah. And now we have here the affine calibrated quantum toric stacks. So I get one cone. I get one cone here. And if I take what is U of the cone and H, and now this is J. This is meant to be J. And well, I get, well, the answer, what should be the affine calibrated quantum toric stack associated to one cone? Well, this is the notation. It's a lot of things in the notation. But what you do is you take Z here. D is still the dimension where gamma lives. You take Z here, and you take M here, and you act by this. Where H bar is the part of H that doesn't send the, I should have said this, and I didn't ever say it. Once I ask H to send, H is doing this, So I can imagine that H is sending the first to the basis. I can always arrange things. I am skipping a little bit, but I can always arrange things so that the first D vectors are sent to the first D vectors here, just to produce the classical torus. And then the N minus D vectors here are sent somewhere else. And that's what I will do typically. It's kind of gauging. It's technical. But anyway, you can write a formula, and then you can check that this is okay. That U sigma HI is the same as UL sigma LH H minus 1 HI, so everything's okay. And so you have a well-defined stack given the data. So if you have cones now, one cone, another cone, and the intersection of the cones, then you have this functor from the category that has cones and inclusions of cones that we will call the combinatorial category of the fan, to the category of stacks, analytic stacks with an action of a abelian complex group. But right now, this gets increasingly technical, so ignore this thing. That is the action of an abelian complex analytic group. And you just think that it's a functor from the combinatorial category of the fan to the category of stacks. And but in practice, what it means is that because of the previous formula, that this is as this is, you can here identify this presentation of this stack with this presentation of this stack. So you can glue these two things. So you can glue all these stacks that are analytic stacks. And a word in this kind of mathematics for gluing is called colimit. So you take the colimit of this functor. That's what it is, but it just means glue all these things. So people say take the colimit of the functor. So you just glue all these things, and then you get a whole thing that is given by the fan, by H, the calibration of the quantum lattice, and by the combinatorial mark points. I stop a few seconds here. Is this believable?
No. I don't know. So it suddenly it escalated very quickly. So
Yeah, maybe examples will clarify this story.
yes, please.
Where it is? Let's do this example. Let's do the quantum projective line. Again, it's exactly an example of this situation. I'll explain. I'll skip this one and go back to it later. So I will use this fan that is a typical fan for the classical P1, that is two rays just opposing each other on the real line. But I will use H, and H, if you remember, in the example that we were doing in the past, we had some H there. H is this. H is this. But here I will put anything, and I will typically put, for example, A, or I could put 1 plus here, a parameter, A, or H or anything, but I think what I have chosen is A. So I do that. I do that. So if A is equal to 0, that parameter doesn't exist, and it's just P1. But if A is not 0, we have two charts. And both charts, interestingly, in this case, both charts, this chart and this chart, are, in this case, Z. Notice that if it was C star, it would just be the quantum torus. But I do the typical thing in Toric geometry, where every cone defines a torus in a particular presentation. But I, of course, partially compactify this torus on that presentation of that cone. And here I do the same. I do C rather than C star, divided by this. I already used the 1 in the H, as Misha said before, is 1 plus Z plus AZ. I use already one set to get a C star, and then I close this C star into a C. And then, well, it's a C modulo this. So it's modulo gamma, essentially. But of course, C star, I call it T here for some reason. C star is inside here. This is the two charts are the same, but I'm going to glue them now. And so C star is like this, and C star is this, but this is this. And then I identify these two quantum tori here. So I have these two charts, and this is if A is 0, well, this is just classical P1. But when A is P divided by Q, then we get these orbitals when A is rational. More interestingly, when A is irrational, then we get a stack with 2 points having a stabilizer, the 2 zeros here, the 0 here in one chart and the 0 here in this other chart, both have a stabilizer equal to Z. And this is not an orbital. It's not even a commutative space. It's not even, as a topological space, it's not even Hausdorff when this A is irrational. So you get this totally non-Hausdorff space, but of course, in the category of stacks, this is not only very nice, it's smooth. Notice that this in the category of orbitals is a smooth orbital. It's not a singular orbital. And this in the category of stacks is a smooth, non-separated stack. It's in fact scalar. So even though the topological space underlying the stack is non-Hausdorff, the stack itself has the notion of holomorphic function. And the basic idea is that holomorphic function, well, it's an equivariant holomorphic function in the charts. Well, you would say this is not very promising, but you can fix that thing by doing some things. And that's the whole point of the theory of stacks, that you can define the scalar form and all these things on this stack that results from this gluing. I don't know if this example helped a little bit.
Yeah, it helps a little bit, but what exactly can you do with these stacks? So can you compute something, I don't know, some topological or geometric invariants to see
everything you can do with manifolds. With scalar manifolds, you can do with these scalar stacks. You have homology and cohomology and everything. Differential forms.
Okay.
All these things. So they are objects that can be studied by the usual methods.
Yeah, for the future, actually wondering if you can draw a tropical picture for those, you know, for this. Will you see anything actually tropically? I think.
Yeah, of course, but it's not hard. Look, P1. Now, what happened is that in the old tropical pictures, we'll see it in P2. It's easier in P2. In all tropical pictures, you always lived in a lattice. You have PN, tropical PN, TPN, and there was always a lattice there, an integral affine structure, right?
Yes.
But now it's about quantum lattices. So now imagine this TP2, tropical P2, we'll see it in the next slide. But now it lives on this quantum lattice, calibrated by H. So you have these tropical curves, but not satisfying the balancing condition. But now they live on this dust. They don't need to live on this classical lattice. You see what I mean?
Yes.
So here is an example of two. Here is an example of P2. And there's 3 maximal cones. The fan looks combinatorially the same as for P2. But now H goes from a Z3 to R2. And every one of the basis vectors of a Z3, of the integers to the third power, goes to the 3 cones in R2. And I'm going to think that one of the parameters is 1 always. And so I only have 2 parameters, A and B. For H, that goes from Z3 to parameters A and B. That it shows the third vector on set 3, because h of 1, 0 is 1, 0, h of 0, 1 is 0, 1, but then h of 0, 0, 1 is some AB that it's on the third direction. Gives you the third direction with the fan. And so here are the matrices that change one fan to the other. And here are the charts. If you take the zeros, you take the zeros out of here, you get the quantum tori. You get 3 quantum tori. But these 3 quantum tori are 3 presentations of the same quantum tori that I write by the star. And the change of variables between the quantum tori are given by these matrix multiplications. I encoded the matrices in an appropriate fashion so that it would give very naturally the change of coordinates. And this is how the monomial change of coordinates would look like in the quantum tori. But of course, B and A could be irrational numbers. And this is how the monomial change of... so you can tropicalize these maps, can't you? But now these are irrational numbers.
Yes, very interesting.
And then you do the same here. You glue this and you glue the charts. And here are the gluing of the charts. And then you get a quantum P2. And this is a quantum deformation. It gives you a whole modular space of P2 as you move A and B. It just gives you a nice modular space of P2 as you move A and B. It's a beautiful space of P2s.
Yes.
But it's very I'm writing the colimits of these functors in an absolutely explicit form, and they are written in terms of these monomials. And this is the modular space of P2. This is the most basic modular space of P2. Of course, I can add more mark points, and I haven't. I could add more mark points, and I haven't here. But I could, and it's very interesting to do it.
Ernesto, Nikita says that he has to go, so
it's a good place to stop right today. It's a good place to stop today.
Yeah.
So let's stop for now.
Thank you so much.
No, thank you.
Thank you. Very interesting.
Yeah, now it's clear. With this example, it's better.
Yeah. Well, I'll continue. But we'll discuss this other point next week. And but anyway, thank you very much, and we'll continue next week. Bye bye.
Bye bye.
Bye.